Hi, welcome to the last unit for AP Physics C Mechanics. In this video, or in this unit, we're going to look at gravitation, but in this video, we're going to look at gravitational forces and their relationships on each other. So one thing is when an object is massive enough, it's going to create its own gravitational field, which can interact with other objects that have gravitational fields. So basically, think about this. All objects have gravity or a gravitational field. They're all going to affect each other. Okay, so Newton came up with this idea that every object attracts every other object in the universe with a force that is directly proportional to the product of their masses and inversely proportional to the square of the distances between their centers. So he came up with an equation that says F equals G m1 m2 over r squared. Now G is a capital G, so sometimes when I write this equation, I'll put a capital G there. It's not our lowercase g. It has a completely different value. It's called the universal gravitation constant. It has a value of 6.67 times 10 to the negative 11 newtons per Newton times meter squared per kilogram squared. And r is the distance between centers. Okay. Now I do want, so one thing to note is that the gravitational force at any distance away from the planet. Excuse me, let me go back. So this is, this equation is for at any distance away from the planet, but the weight equation is at the surface of the planet. So these are both, weight and this equation are both gravitational forces, if you want to say, but the universal gravitation is the one when you go away from the planet, whereas this, the mg, the weight equation is on the surface of the planet. But you can use that to solve for the g value. So I can simply say, okay, if I'm at the surface, right, if I have an object at the surface, this is true that my gravitational force that I experience from the planet is equal to the weight of the object. And I can do some simple substituting here. I don't know why I put an F there. It should be a G. That's why the equation looked weird. Red. I'm starting to write F here. All right, so the G value on any planet is simply the gravitational constant times the mass of the planet divided by the radius of the planet squared. And so that's something that I like to ask, give you, and this, you can do relationship type questions, right? Planet X is 5 times greater than Earth in terms of mass, but half the radius. What's the G value on the planet? And so you can do, factors of 1 to figure that out. And another thing to note is that gravitational force will decrease rapidly as you leave the surface of the planet because it is an inverse square law, right? So Fg varies inversely as 1 over r squared. And so as you can see in this picture with the Earth, the arrows are getting smaller as you're getting further away. So the greater you feel the greatest gravitational pull at the surface, and then as you go away from the surface, you start feeling less of a pull from that planet. Now, this graph is very important to note. So outside, off the surface of the planet, right? This is our 1 over r squared relationship, but this one here, okay, is a linear relationship, and I may have written that equation down wrong. So inside the planet, it's a linear relationship, and I think I wrote the equation down wrong. I will get that, and I'll post that into the comment section about what the equation looks like. So let's look at an example problem involving, and this was the example problem we're going to do is over the 2 videos. It was actually an old AP free response question on this topic. Okay, so in March 1999, the Mars Global Survey, or GS, entered its final orbit about Mars, sending data back to the Earth. Assume a circular orbit with a period of 118 minutes or 7,080 seconds, an orbital speed of 3,400 meters per second. The mass of the GS is 930 kilograms. The radius of Mars is 3.43 times 10 to the 6th. Calculate the radius of the orbit and then calculate the mass of Mars. Okay. So we have to attack this a couple of different ways. So you have to remember that, so when an object is in orbit, it is in a circular orbit. So the force it experiences, or the net force, is our centripetal force, so mv squared over r. So we need to figure out, right, it wants us to find the period of, or the radius of orbit, right? So we actually have to use our equation from, an object in circles is going to travel the circumference of its path in the time given to us, right? And so we just simply do VT over 2 pi. That'll give us the radius of the orbit. So we don't have to convert anything. They gave us all the info that we needed. So 3,400 times 7080 over 2 pi. That's constant. And so the radius of the orbit is going to be 3.83 times 10 to the 6th meters. Okay. Now, that doesn't mean that's the height off the surface, because in these equations with planets especially, and we'll address it in the next one, the radius of orbit is the radius of the planet plus the height. So that R0, or R sub O, that is the R that we actually just calculated. So if we wanted to find how far off the planet it was, we'd have to subtract this number that we just calculated from the radius of Mars. Okay, because the way you think about it is, here's Mars, here's our orbit, right? And what we actually found was this value, not that one. Okay. All right, so now let's find the mass of Mars, because we can do this with this calculation, right? With this equation. So we know that the force that the surveyor is experiencing is mv squared over r, but it's also the gravitational force, right? And again, r is the distance between the centers, so the mass of the cancels out. This r cancels one of those r's, and so the speed is simply gm over r, right? So speed squared. But we want the mass of Mars, so we're going to say mass equals rv squared over g. And the r we're using is the orbital radius, right? Again, the distance between the centers, right? And we're going to divide it by 6.67 times 10 to the negative 11. So the mass of Mars by our calculation is 6.64 times 10 to the 23 kilograms. Okay. All right. So we have one more video to do, and that will conclude AP Physics C for you guys. Where we're going to look specifically at the orbits of planets and satellites. This is something that doesn't generally cover in an algebra-based course, but it is covered here in AP Physics C.